This is a research project by myself, Colleen Gavry-Luke.
And myself, Zach Ramel.
This presentation will be covering pathfinding for dynamic environments, which are environments not fully known or changed during path traversal. We will be talking about A star for dynamic environments and why it sucks. Then we'll be covering an improvement on A star called D star Lite. Next, we will be demoing both algorithms side by side. And finally, we will cover applications of the D star Lite.
A star, as one of the best general purpose pathfinding algorithms, seems like a good starting point. But when pathfinding in an unknown environment, it has some issues. Any pre-computation optimizations that are normally applied to this algorithm just don't work, because if you were to do something like jump points search, you just wouldn't be able to calculate any of them. You wouldn't have full knowledge of the map, and if things change, then it invalidates all of those optimizations, and trying to recompute them on the fly is more expensive than just not doing them. The general algorithm for using A star in a dynamic environment is called A star replanner, and it generally just involves running A star, and then anytime that something invalidates it, it reruns it, which sounds inefficient, and it is. So here's an interactive look into how A star replanning would tackle a pathfinding problem like the one laid out. In this scenario, the agent, as the small purple guy, only has awareness of anything in a bounding box around a size 5 by 5. So anything outside of that, it's just not aware of, and it can't take into account when pathfinding. Um, if it gets close enough to something, then it will become aware of it. So with the information that it has, it can attempt to make a path, and it'll find an invalid path, but it doesn't have any way of knowing that the path that it created isn't valid. And so that's a full A star path computation only with the knowledge that it knows. And so as it begins moving along its path, it will discover that there are actually cells there that are in the way. Like here, it can't cut that corner, and so it's discovered that that path doesn't work. And so how do you tell an A star pathfinder to replan its path? You don't. You just redo the entire pathfinding from your new starting point. And so there's another path computed here. It's also invalid, but as it moves forward, it'll find that that path was also invalid and then have to replan. So another path has been made. And so here, it's moved, and the cell that it's encountered has caused it to invalidate its path, even though it doesn't affect its path. But it has no way of knowing that. It just has to replan because that's all the information that it has. And so that path gets tossed, and the same one gets recomputed. And then as it moves again, the same thing will happen. It'll have to invalidate its path and recompute the same path. And then now that it has full knowledge, enough knowledge to get to the goal at least, it will be able to just get there. And the cost of that in total is 4 paths, fully computed.
Next up, D star Lite will be covered. As A star is a revolutionary algorithm, being one of the most versatile and simplistic pathfinding algorithms, it is seen as a gold standard for pathfinding. This is of course because A star makes many assumptions about the environment it traverses within. To remove many of these assumptions, D star Lite was created. It's now restricted by the requirements of A star. Due to this reduction of restrictions, D star Lite has many applications in the real world. While the idea behind the algorithm is simple, the implementation details in mathematics can often be complex. Therefore, instead of just explaining this code that's on screen, we will be giving an intuitive explanation of this algorithm.
So in this look at how D star Lite handles pathfinding, we're giving it the same initial conditions and the same parameters regarding obstacle awareness as the A star replanner. So in addition to keeping given costs for each node, as Dijkstra's algorithm and A star do, D star also keeps a measurement called RHS, which is a parity cost designed to determine if a node is currently consistent. And consistency is a measure of if something has changed and in what way. And depending whether the given cost is greater than or less than the parity cost, D star will either set them to be equal or take the minimum of the neighbor's parity costs, which will propagate any changes in node costs. So the initial planning phase of D star Lite will set up a gradient of costs across the problem space, and then the path will come from the goal back to the beginning, and it'll just come from seeking the lowest change in the gradient. Um, so you'll get a path just like that. So as the agent begins walking through the path, it'll encounter cells with different costs than it expected, and uh, each of these cells will need to propagate their changes into the gradient, uh, and that'll start creating those inconsistencies and modify the gradient, which will implicitly modify the path. Um, so after every inconsistency has been resolved, then the new path is there. And so that's a step we call gradient resolution. And so then as it continues moving throughout the path, uh, every newly changed cell that it encounters will again create inconsistencies in the gradient and propagate their changes. And so a new path will arise here. And as the agent continues moving, this time when it encounters a cell, the changes that this cell makes to the gradient don't actually affect the path, because even after they propagate, they don't touch any of the cells that the path is. And so the path just remains the same. And then with no further remaining information, it is able to finish its pathfinding. And so in this case, it did take the exact same path as the A star replanner, but it did a lot less work. This computed the one full path over after doing the gradient, and then two path affecting gradient resolutions. Only two of them actually touched the path. But the A star replanner had to fully recompute four different paths. So there's a big performance win here. So there's not any real difference between cells changing as the agent discovers them, or like as they become visible to the agent, and cells that change because they just changed, like a block was built or a wall was broken or a door was closed or opened. Like they're really the same thing, and so it works for both limited amounts of vision and dynamic environments, or both combined.
Next up, we will be demoing the application. But first off, let's explain what you'll be seeing in the demo. This is a screenshot of the demo application. On the left is A star and a partially explored environment. Similarly, on the right, D star Lite is being demoed. At each iteration, the algorithms wait for each other to allow for easier comparison. As for color coding, blue is empty / unexplored space, black is seen walls, shades of red are the open and closed list, depending on how the algorithm represents them, and finally, the yellow lines are the current optimal path. This is the demo application. As you can see, both algorithms are exploring the environment and saving wall data as they're either blocked by or passed by. A star starts off very greedy, creating suboptimal paths initially, and improves as the time goes on. Similarly, D star does the same. In fact, D star acts as A star would in fully known environments. The benefit here is, of course, D star's ability to adapt to these changes in environments, these walls that it's starting to see as it moves on, while A star must recompute the entire path every single time any change occurs. You may notice that the paths slightly differ. One reason for this is because D star starts off from the goal, while A star starts off from the starting node outward. This is just an implementation detail. Overall, now that the map has been starting to fully get explored and mostly known, both algorithms look roughly the same, and that is, of course, due to the fact that D star is underlying based on A star. Next up is applications of D star. Here are some Real world cases where A star cannot be applied very well, such as agents in dynamic terrain, where the terrain changes as you walk through it, or you can't actually see the entire terrain. A good example of this is a maze, a robot in a maze. Some fault safe applications where if some node graph breaks in the middle, you have to fix it very quickly, and it has to be very uh, robust. And further real world applications, such as the robot in the maze. So agents in dynamic terrain, a good example of this is mobs in games. Well, they're walking around, especially voxel games, where the terrain can get modified constantly. The player can be running around, breaking blocks or voxels, and the mob must then pathfind through it. You can reuse old pathfinding data to speed this up and also make your game allow more mobs. Another example is packet routing, where speed and efficiency requirements are very key because nobody likes packet drops, nobody likes, delays in internet routing. So you got your connected node graph, which D-Star Lite can also be applied to. And of course, if any of these nodes suddenly drops off, then D-Star Lite can quickly recover and not drop many packets. Finally, and a good example of real-world applications is the Mars rover, where the terrain it traverses is very noisy. Input from the sensors about where it's going, what can it can see, the dust storms, and also it's a partially known environment because it only knows so much about where it is and where, like the path to where it's going. So it has to be able to adapt.
So due to the nature of the D-star algorithm being mathematically and implementationally complex, we did a lot of research to figure out how to implement it ourselves, and yeah, use these as references. Thank you very much.